For the last two FRQs here, we're going to be considering a pendulum and what happens to various quantities as the string gets longer. So for question number 4, we have students constructing two experimental setups, A and B, as shown in the figure. Each consists of a small block of known mass M attached to a string of negligible mass where the string in setup A is shorter than the string in setup B. Tops of the strings are fixed in place. The blocks are held so that the strings make an angle theta with the vertical, and the blocks are released from rest. So for part A, they remind us that the angular momentum of a mass M moving with speed v in a circle of radius r has a magnitude of mvr about the center of the circle. When the blocks are in motion and the strings are instantaneously vertical, is the magnitude of angular momentum about the fixed end of the string greater for the block in setup A, greater for the block in setup B, or the same for both sides? So the answer here is that the angular momentum is greater for case 2. Right, and we have 3 things to consider: M, V, and R. So the mass is I shouldn't have put a arrow there. The mass is the same for both, so we don't have to worry too much about that. The radius is larger for case 2, but we can't just say that. We've got to consider the velocities as well. However, we're going to use mgh equals 1/2 mv squared here. So our velocity is equal to the square root of 2gh. We've done this before. The object on the longer string is going to have a larger vertical drop. Okay, so its velocity is also going to be higher. So since the velocity is higher in step 2 or case 2, and the radius is also larger, our angular momentum is going to be greater for case 2. Now that was kind of A and B together. Part A says which one is it. So you get 1 point for part A, case 2. Then part B is actually the paragraph where we justify things. So we get 1 point for saying that we have a greater height drop for a longer string. 1 point for saying that since we have a greater height drop, that means more kinetic energy at the bottom of the loop. 1 point for using MVR to compare the angular momenta. 1 point for saying that both V and R are larger in case 2. And then 1 point for the logical relevant argument. So that's the paragraph for part B. Part C says, we have a kind of a do-over for part C. We have the same thing in the next problem. So another setup is created, this time with 2 blocks of equal mass that are taped together. At the instant the string is vertical, the tape fails and the bottom block separates from the top block and falls to the floor. So in that last case, they have a pendulum and a projectile going at the same time. Interesting. The top block is still attached to the string and reaches the highest point of its swing before the bottom block reaches the floor. That's important in a couple of the questions we have to deal with later here. So C says for the block's Earth system. So gravity is an internal force here, just to put that in your head. Is the total mechanical energy of the system immediately after the blocks are released the same as, less than, or equal to the energy when the top block reaches the highest point of its swing? Now, I think that question is missing a few words there, but that was the way I interpreted that. Is the mechanical energy of the system the same after the blocks are released as it is when the top of the first block reaches the highest point of its swing? Now, remember that the bottom block is still in motion when the top block reaches the top of its swing. It told us that in the paragraph there. So since no external forces have acted on the system yet, the mechanical energy is conserved, okay, even though the blocks have fallen apart. Since we have the block's Earth system, gravity is internal, so the gravitational potential energy of the blocks and the kinetic energy of each of the blocks, all of that is conserved. So part C is 1 point for yes, plus the attempt at an explanation, and then 1 point for saying no external forces. Right, then part D says consider the top block and assume the size of the block is small compared to the length of the string, so that the center of mass of the top block is not appreciably different from the center of mass of the original two blocks. The point there is that the string isn't getting any longer. Okay. Indicate which of the following time intervals is longer, if either, if the intervals are the same, right? The same. So interval 1, the time interval from when the blocks are initially reached to when the string is vertical. And then interval 2, the time interval from when the string is vertical to when the top block reaches the highest point of its swing. So what they're saying here is that here is interval 1, and then here is interval 2. So what they're saying is this swing up going to be any faster than this swing down because we've lost half the mass here? And the point here is that the period of a pendulum doesn't rely on the mass, okay? It only depends on the length of the string. So that mass falling off and going to the ground is not going to make the pendulum swing any faster, which is possibly what they want you to say. The reason they made such a big deal of saying how the block is small compared to the length of the string is because they're trying to tell you here the length of this string is remaining constant. So the answer is that those intervals are the same, and that's 1 point for that, and 1 point for saying that the mass of the bob doesn't affect the period, so losing half of the mass doesn't do anything in this time swinging down and the time swinging up are identical.